And we are going to talk today not exactly about the inner mechanisms of the in-memory data fabrics, but we're rather going to talk how to apply the beautiful ideas around the in-memory compute and in-memory storage towards a much more mundane problem of the data processing, right? So I came from a distributed background myself. I was working in Sun Microsystems on distributed systems for a while. I've been developing software-defined storages, as you know, as HDFS. And over the years, I was sort of drifting towards the convergence between big data and the fast data. There's a lot of cables here. Hopefully, I won't trip. Right, so if you follow in the Hadoop development in any sense, so you probably seen some of my work outside, including the co-authoring of the book on the professional Hadoop. And anyway, so today we're going to talk. I will start, and then Alexandre BOUDNIK will continue from the slightly different angle, looking at the same problem. We're going to talk about the modern data architectures, data processing architectures. We're going to talk about how in-memory data fabric can complement the data processing architecture and data processing platforms. We'll talk about the concept that we have came up, I guess, a year and a half ago, a couple of years ago maybe, that we decided to call Iota architecture, and I will explain why in a second. And Alexandre will be talking about some of the practical, well, practical is probably not, is not applied cases, I would say, applicable cases of the in-memory data processing systems for a variety of the challenges that you can see in the market and in the industry. And some of the use cases would be covered as well. So again, considering the fact that the weather is beautiful, and if somebody wants to just hear the essence of this talk and save yourself 40 minutes of the life and go and take some sand bathing, I'll try to explain to you literally in one slide what this whole fuss is about, right? And so first of all, you never have to, you never should separate the batch processing and the streaming processing, right? So when you look at the modern computing architectures, you see a lot of the attempts to cross this cognitive dissonance chasm where people are processing the historical, sets of data one way, namely in the batch fashion, and near real-time data, or the data that comes from whatever streaming sources, using completely different sources. It's completely different platforms, different compute engines. So this is the bad idea for a variety of reasons. One of them is the framework impedance, complexity of the programming models, and we'll talk about the rest of them in a second. So clearly, compute should not be separated from the data. You should collocate it. It's a lesson that has been learned in a hard way in the big data platforms, particularly in Hadoop. And Hadoop was so efficient because you could easily scale the compute code towards the data and process massive amounts of the data in parallel, achieving actually huge horizontal scalability. Clearly, when you deal with the data, no matter if it's a big data or small data or whatever data it is, data by itself, data at calm or at stay, is not much of the value, right? So you need to do something with the data. Sometimes you have to change the data, sometimes you have to enrich the data, transform it and stuff like that. And you have to definitely track the data mutation, and we'll see in a second about a very interesting concept around this particular problem. And again, when you deal with the data, if you have the multiple copies of the data, it causes data concurrencies, and then dealing with the concurrencies of any sort is very hard, specifically when you deal with the data concurrency. It's hard and annoying. And again, there is an elegant sort of solution for that. So the rest is a mere detail. So for those of you who want to, do the tanning outside, you can go. I won't hold it against you. And this is your final warning, so I will proceed. So when the Greeks were, this joke is so boring now. I've been repeating this like 6 times in the last 3 weeks, I guess. I'm getting tired of it. But anyway, when the Greeks were doing their alphabet, inventing the alphabet, putting it together, they clearly didn't foresee the fact that there is going to be a bunch of the geeky computer scientists that will use the Greek alphabet to call everything and everybody and his uncle with the Greek letters, right? So clearly, when you come to the computer science, you'll see the whole bunch of the lambdas. Not of them are equal, but there's many of them, right? So, well, first of all, from the functional programming, there's a lambda in the way of the anonymous function. So you can serialize it, you can pass it around, you can assign it to a variable, you can query it, you can deserialize and execute later, you can do a lot of wonderful things with it. Fortunately, we now have it even in Java, although Java is not the functional language. Well, it's not a dysfunctional language either, but at any rate, so the other lambda is lambda in the sense of the platform as a service. You can define a function, you can send it somewhere, and it's going to be executed somehow following some event trigger, right? So AWS Lambda is probably the most famous implementation of it, but there are others like Cloud Foundry and so on and so forth. So clearly there is yet another Lambda which has been used for a while in the data processing industry, and it's called Lambda architecture. And effectively it consists of 3 main layers, right? So the layer number 1 is the batch processing layer, a slow one, right? So you have tons of the data, you run some stuff like Apache Hive or Apache MapReduce, Apache Hadoop MapReduce, or something else to process these, tons of the data and trying to figure out something, right? Calculate some inference coefficients and stuff like that. So the other one is a speed layer, and the purpose of it is basically trying to process the data that comes as it goes, right? So you listen to some sort of message queue or whatever it is, you get the data out, you get the events out, and you're trying to process it. You can do complex event processing, you can do machine learning with it, things, right? So Apache Kafka is probably one of the good candidates for the implementation of the speed layer. And now with Kafka Streams, you can do actually some processing in it. Well, the issue with that is once you process the data in the speed layer and you process the data in the slow historical layer, batch layer, you have to somehow get to the point where results are actually making sense when combined to each other. So for that, you have to put together effectively the servant database or reconciliation layer, which sort of tries to put together the coherent picture of the world and present it to the client application or user, right? So normally, again, in the world I live in, and probably most of you too, something like Apache HBase would be used for that purpose, right? So the properties here, effectively, that architecture is introducing is that the data flow is immutable and unidirectional, right? So you always get the data from the speed layer, you store it into the historical layer, and once in a while you restart the batch process in a historical layer to kind of get the complete view of the universe and augment it with whatever you just derived from the stream. So, as I briefly mentioned before, there are some drawbacks, of course, in this approach, and complexity, data accuracy, and operational overhead are just among a few of them, right? So, and when I refer to the data accuracy, I explicitly have in mind the batch edges issue, right? So basically, you cannot guarantee that between the two, once the batch is done, fulfilled, all the information relating to a particular event is inside of this batch, right? So there is a chance that a piece of the data could spawn to the next batch, right? So it depends on how arbitrary you're choosing the cutoff time, right? And because of that, you effectively can step on the data accuracy issues. Okay, so, and clearly people weren't sitting on their behinds doing nothing. They were trying to improve this. And they said, hey, actually some Lambda are kappas, right? So let's move on and have another incarnation of this Lambda thing. So another one coming effectively from somebody in Netflix, I believe, right? So they came up and said, hey, let's do this kappa thing, right? So instead of doing the batch processing in the storage layer or in the historical layer, let's consider all the data to be streams, right? So historical data, effectively, whenever you need to process it, you just restream it from the long-term storage, right? And normal streaming data would be processed as before. So effectively, again, you have a streaming source, you have a stream processing, and you have, of course, this serving database, which in this particular case would be much simpler just because it has to work with the streams only or the results of the stream processings only. And effectively, every single streaming job could dump all the results into some sort of the intermediate table inside of the serving database, for instance, right? So in case you need to reprocess the data because the code has been changed or something happened, so you effectively do historical processing as a stream, as I said, right? And if you need to make the changes, you just reprocessing first historical data, and then you start processing the data that comes from the stream, right? So it's sort of like an attempt to catch up running the reprocessing at the higher speed in order to get to the point where the current stream data is, right? So complexity is significantly lower because effectively you can use just the one processing engine for everything. However, the restreaming of the data, replay of the data could be an issue in some cases, right? So which is not probably the best part of this architecture. But compared to the last one, it's way better. So when you put these things next to each other, so what you see is effectively that's the Lambda, right? So there is a slow processing and fast processing, and it got to the certain DB, got reconciled. You can read it, you can use for whatever to build the data marts or whatever you want to do with it. Now the Lambda is slightly different, so you feed in the events into the streaming job, and here's your streaming job on top that is doing the processing right now, right? And if you ever need to do the processing, this the one at the bottom started processing the historical data. Once it's catch up with the current point in the stream with real-time data feed, we effectively, what we can do is just yank the older job out of existence, remove the intermediate results, and effectively the new one becomes the main processing stream, right? So it's a little bit simpler from every single point of view, in the sense that you don't need to cross the programming frameworks barriers. Oftentimes, actually, you don't have to use different programming languages. You never leave the same stream processing system for whatever you need to do, right? So no matter what, you sitting inside of the same, say, Kafka, right? And you're not going anywhere, or Flink, maybe, whatever. And I should, of course, say Apache Flink. So now stepping back a little bit, and that I'm sure is going to be boring like hell to most of you, because this is in-memory data fabrics, and everybody here aware about this, sorry. But I will spend 30 seconds on this. So in-memory data fabric is effectively a very old, simple separation of concern implementation, right? Or the implementation of the idea of separation of concerns. So all you have is a bunch of the sources. You might have software-defined storages, data warehouses, and so on and so forth. On the other hand, you have a bunch of the consumers of the data, right? And that could be exploratory data, APIs, REST, whatever, SQL and stuff like that. But the trick is, of course, in the middle, where you have a bunch of the computers sitting together and co-locating the data storage in the computer RAM and the compute and a lot of different things such as distributed services and what's not, right? And this middle part is actually, as we will see, play the key role in this Iota proposal, because it can do anything in one place, and you don't actually need to go anywhere and change anything, right? So, actually, let me do just this. I hate this animation, by the way. Here we go. So data fabric is effectively a unified way at all of your enterprise data, right? So multiplicity of sources are connected to one medium, and you can get the data into this medium and process it across different applications inside of this compute layer, no matter where the data came from, right? So it's a layer for data access. It has low redundancy and very few data movements because the data is already sitting where it has to be processed, right? So you don't need to make multiple copies of the snapshots of your data lake and this and that. So the data is there. You can do with it whatever you want to. You can, even if you're brave enough, apply the right true caching, right? So once the data got changed inside of this in-memory cache, you can try to actually write it back to the source. Of course, you can break many things if you don't know what you're doing, but you know, it's your funeral, right? So the computing medium is affinity sensitive, right? So it tries to process the data where it is on the same computer where the data is stored in the memory. It's highly available, of course, and fault tolerant because it has to be distributed and able to do the compute. And of course, there is a variety of APIs and very tight integration, native integration, I would say, with the big data, such as Apache Spark, HDFS, HBase, you name it. So you can use this storage as the persistent layer, essentially, for these compute frameworks, right? So machine learning frameworks and so on and so forth. So and here I present to you intention the Iota, right, itself. Again, with all I said, that would be pretty trivial. But here we go. Here we got the in-memory data fabric. Here we got the bunch of the sources, right? You probably can add more. I'm not that creative. So you have your events coming from here and there. And clearly the data from different data sources are coming at a very different speed. So as the result, you might have to process it in different fashion, right? So some of the data have to be processed in a transactional sort of way. And Alexandre will be talking about why transactional processing in a distributed environment is a huge pain in the neck. You can process some of the data in a close to real-time fashion, right? So some of the data has to be processed as a complex event processing on stream and stuff like that. So, and fortunately, because all the compute is actually living effectively on the same set of the nodes, right? Same framework, same cluster. Some of this data would be processed with, say, in-memory MapReduce, right? Some of the data would be processed with real-time sort of workloads, right? But because of this distributed cache that is common for every single application sitting on the cluster, every single service sitting on the cluster, you can actually literally easily exchange the data between different entities, application entities, without much of the, as I mentioned before, application impedance, right? So you don't have to serialize the data every single time. You need to pass the object from, gosh, I don't know, Hive to HBase, for instance, right? So you don't have to hit the disk, you don't have to hit the persistence, you don't have to serialize it and send it over the network, right? So you get a tremendous performance boost from here. And again, you can keep on adding variety of the applications on top of that just in order to actually enrich your environment. By the way, this is probably the most sophisticated animation I did in my life, honestly. So, okay. So we spoke about these couple of points, right? So that's sort of covered. Now I will pass the microphone to Alexander. He will be talking about the data mutation issues and data concurrency issues, and about some of the practical applications or how to solve certain challenges in practice using this particular approach. With that, thank you very much. Alexander?
Hello, everybody. My name is Alexander Boudnik. I'm working for EPAM. In my previous life, I have to bring watch glasses. I used to be a computer scientist, writing SQL parsers, compilers for different languages, even SQL optimizer. But recently means like, what, 8 years ago, I started working with big data. At that time, big data, the word big data does not exist. Now we have words. Now we can talk about it. And so let's go and talk a little bit about common issues with the data processing in virtually any industry. So we are working with states, persistent immutability, or which is much worse, mutability of the data. The biggest problem here is sometimes we just misperceive the primacy of the data. Let's say you have a data source and data from it copied and copied over again into different data storage. And I'm talking about really like bloody enterprise. And in some period of time, people just lost a understanding of what actual state of this piece of data. Is it sacred data? You cannot erase it, and how actual this data is, and what about versions of data structure, versions of processing programs, how to provide access for the for bunches of application. Some of them, you know, I'm afraid to use this word, written in COBOL. Yeah, but actually, with all respect, it's quite unusual programming language. And we also have other operational issues like security, like provide the access, and more important, forbid the access to certain pieces of data for certain people. And also, we need to think about this boring stuff, ETL, ELT processing and publishing. And finally, about data grace, how to drop the data, or should I say, dismiss, not dismiss. Yeah, dismiss the data. All those issues are very serious, actually, and my own conspiracy about one of the reasoning for appearance for existence of big data is high market demand for ETL programmers, because it's quite boring job, and not everyone wants to do that for all his or her professional career. And one wise man from a New York Stock Exchange, he said that all what we do here is acquire and store. Acquire and store. This looks like a mantra. So if I, stop talking these lyrics and we'll go on little bit more practical thing, I will talk about the same ideas that Konstantin already unveiled. And actually, the word Iota architecture happens right on previous in-memory computer summit, I believe. Yeah, since that we tried to popularize it between a few conferences and our clients, and now you hear it. So let's talk about two breeds of data warehousing. One is classical one, which you probably need from Ray Kimball's books. It's update-driven warehouse. When you pull data from different data stores, do some maybe normalization, cleansing, and ETLing or whatever, and then store it in a database where you can do joins and all other funny things. Versus other heterogeneous query-driven data warehouse where you don't store actual data. We just store a definition of how you will access the data. And maybe some like ETL processing to do this normalization and cleansing each time on demand. Both those approaches have their drawbacks and have their good points. For example, heterogeneous data warehouse, query-driven data warehouse, it follows the single source of truth principle, while update-driven data warehouse does not, but it provides a convenience for joining. And of course, both heterogeneous query-driven data warehouse require a much more network bandwidth, because this data shuffling happens again and again. If we think how big data could help, and actually, this query-driven approach very in line with some practices of big data. We can see that on-demand extraction, also known as a schema on read or parse on the fly, or using a multi-structured data, works here and allows you to avoid the complex ETL. Also, by partitioning and by collocation and share nothing, we may provide a better performance on in a queried data warehouse. But to automate such technique and to hide the complexity of this data warehouse from application or programming, you need to make it pretty much metadata driven. So the metadata structure should be sophisticated. So let's talk a little bit about what data we are working with. And the main distinction between a primary and derived data. The primary data is non-deterministic, cannot be reproduced. So it's, for example, during this presentation, the temperature here maybe goes up and down, or sound level goes up and down. Unless you record this, you cannot reproduce it anyway. So, of course, to make it usable, you have to persist this data. And by definition, this data is immutable once it happens. Another one is derived data. It's or deterministic data. It could be reproduced exactly over and over again. So if you want to process any of primary data, let's see, calculate the average temperature during the day, or calculate, I don't know, just a sum of numbers in the sequence, you can do it easy. So this data is immutable because you have the same result, but it's ephemeral in their nature. So if you kill this data, you should to pay some price, of course, to reproduce this, but you can reproduce it exactly with the same bit by bit. And we have two other kinds of data. It's a versioned metadata with all the, by its nature, persistent and immutable. And we have a code which is also persistent and immutable. So if you see, there is two columns here by, say, persistence, another immutability, and you see that only derived data is ephemeral, but all this data is immutable, which is great. Which I would call it, with all my modesty, I will call it a discovery. You see, so it's immutable and stateless. What benefits of stateless we can get? We have no concurrency. It only when you put a new version of the data, there is some concurrency in the catalog, which very actually mild and could be mitigated easily by implemented of Redux multiple partition technique. You may leverage paradigms of functional programming easily, because you see Scala becomes so attractive sometimes because of that. I personally don't like Scala, but anyway. And you may, again, as I say, you may understand I hate an ETL. So by putting these pieces of code which executes on the fly in lazy manner, you actually avoid the stationary of this data. And as we say, okay, what's the moving part of proposed query-driven warehouse like Iota architecture data fabric? It contains of main storage or bigger storage, which is write once, read many. It's a place where you store versioned metadata, versioned data, versioned code, and they have transient cache store where you store derived data. And you have computer engine, which can read anything and put the results in a, do of course some intellectual stuff, I hope, and puts result back in a cache. And when you store results in a cache, you store it, okay, I'll tell you. Okay, so how to read less? In traditional SQL environment, you can use either a technique called indexing or partitioning. Indexing works well for pinpoints to queries, and when you start reading, when your output is significant, it exceeds few percent of it, indexing doesn't work well. You have to think about more static chopping data in the pieces. And this is a technique called the partitioning, and this is the typical partitioning structure on on the left side of the screen, yes. On the right side of the screen, it's a patchwork made of a bunch of different pieces, different colored pieces. It's actually patchworks. It's a variety of data block, and each data block is a similar object limited with a fixed dimensions, right? And you stitch them together in an arbitrary set of the data. And I would say more than, for example, data frames, you know, this popular interface, it's very well suited to represent individual data blocks. So, data blocks and data catalog, of course, we have to keep it somewhere. And that's, I would say, distinct the proposed architecture from many things that claim they are data lake or something like that. It's a more data swamp. So, that's a definition of the data blocks, and we developed the structure how to present any data block as a set of, as a sum URLs, which could include, of course, with a custom protocol handlers, which can include reference to the file, to the web services, to the sites, to the even to the SQL queries. And data catalog, of course, it's organized those data blocks and patchwork. And when you're talking with the system, you have a different APIs here. You see, you have a data API, metadata API, and version API. And by going that, you say, I need that set of data blocks in a particular place. And it works like a charm, like make. It will do anything you need to bring your data in a location you required. If the data already here, you just get access immediately. So to do that, we introduce a cache. Cache is very popular and very intuitive thing. So by doing this calculation once, you stash it in somewhere just in case if you need this calculation again and again. So in this particular case, you put the function call, serialized function call as a key in a key value store. And as a data, you store the actual data blocks or sequence of data blocks that this function call returning. We already add some statistics just to optimize, or actually just to be able to run eviction policies, which will actually discard the data blocks from this precious memory. And you can control, of course, all the retention and apply policies about data lifecycle. So some few other aspects, because you are tracing all calls to obtain the data as a byproduct of the execution of your data, of obtaining of building the data blocks, you can build a full dependency graph of all calls that are used to build this data block. And so if some pieces of this dependency graph are missing during, let's say, mistake, during eviction, or because of you have a new version of the data, you can easily invalidate everything in the cache and do this recalculation. Yeah. In that's way, I mean, okay, I have to probably show this line first. So invalidation in lineage, it's driven by dependency graph. And pretty much what we have implemented, it's just a memorization pattern. When you have cached results and you track dependencies, in case if something upstream get changed, you may invalidate all data stream, but it's ready to repeat the lazy evaluation, which will bring or exactly the same result or maybe new version of the same result. And if talking about scalability, It's interesting because when we start doing experimenting with this and doing some POC, we understand that, you know, answer is just get a bigger hammer or put more boxes if worm uses. So if you have need more memory for primary storage, put more boxes. If you have more capacity for in-memory data grid on a cache and calculations, put more boxes here. Talking about use cases, I already mentioned the data lakes. That this approach may bring something really useful to data lake metaphor. You may, you know, reduce memory shuffling. You make a easy integration with legacy. Real-time personalization. That's what recently machine learning robots do. So you can make a ML-driven CEP when machine learning brings models into the context of CEP processors. Or you can, and actually this model was used already for fraud detection for one of the exchanges. And again, I would emphasize the benefit of Iota architecture. You can read it, of course, but I would say one of the ideas here, again, avoid transactions if as much as you can, avoid states, and collocation and share nothing principles are rules here. And now, Konstantin, could you join me? And maybe if you have some questions, please.
And before we go to the questions, I have to personally apologize for the horrific color schemes on some of the slides where you couldn't read things because, you know, they were so close to the background. It's totally my fault, so don't blame anyone else. Anyway, questions. You have 11 minutes.
So I think I have hypnotized the auditorium. Like
hey, wake up, everybody! Wake up! Or either we just did a good job explaining everything. So
yeah, please.
You had 4 lines where you said everything's immutable, it's all good, therefore I'm statements, great. Your second line was where you built predictions or derivations of your amount of data, your immutable source sensor data. How often are you rebuilding those predictions in order to keep latent data latency low in terms of age of actual queries?
So I guess if I heard you correctly, the question was, first of all, there is the immutable primary data, and second of all, there is the derived data. How often you have to recalculate the data to come from the state number 1 to state number 2, right?
Yes, so I mean, if you're following a traditional event source model, like if you're using a Kafka topic or something, so you're taking a historic series and you're taking events against your data and using that to build a projection query. You have to keep that projection up to date. You either need to kind of do it in line with your events arriving or periodically batch mode, where a batch is kind of a predict word in the story. So are you keeping that projection very tightly coupled to your inbound events and the way they change those in your projection, or are they computed periodically to support your queries?
Again, if I heard you correctly, and I'm sorry, it's a little bit quiet and I cannot hear everything. Yeah, but I guess no. I guess I got you what you're asking. So whenever we need to recalculate the projections and how often we need to recalculate the projections, it's actually not a platform decision. It's an application decision, right? So it depends on the eviction policies. It depends on how readily the data is available in the cache, or when the results, because of the dependency graph, right, got invalidated just because some of the pieces of the data in the dependency graph got changed. The recalculation would happen, and again, the lazy evaluation would be used for that.
So it is completely, yeah, it is completely on demand, and as soon as application require some data, and it will do it each time before running the actual processing, you see everything will be got checked. And I didn't mention that data blocks also protected with checksumming, so even accidental changes would be really detected. Checksum stored in a data catalog, so we can find the corrupted blocks and recalculate them.
Don't be shy. No? Going once, twice. Thank you very much, everybody. Thank you.